Now, flange beam, I'm going to cover mainly the when you can consider the flange of the beam, which coming from the slab. Okay, but what the beam that you need to design, you can always design only as rectangular beam, but under certain conditions, you can consider the beam as a flange beam, which is together with the top part from the slab, together with the beam, it forms like a T shape or L shape. Then I will go to the design formula, the steps that you have to go through. So design for flange beam has two parts that we need to consider. One is design for flexural reinforcement. Okay, and then for shear also, when it is a flange beam, there are special considerations that we need to look at. So that is the thing that I'm going to go through with you by going through the steps. Okay. Now, first of all, so flange beam is actually, um, we take advantage of the slab which is cast together with the beam. So the shape can be either L sections, L shape. It can also be T shape. Okay. Now, because we want to take advantage of the slab, so there are conditions that is where we can consider the beam that we want to design as L shape or T shape, which is we consider the contribution from the slab. Now, here I show here, this is in your notes, part of the flange beam design. Now, here is part of the construction process. Here the beam is cast first. The beam is cast first. Then after that, only the formwork of the slab is constructed. Then only you cast the slab. So in this case, beam and slab are cast separately. So if this is the case, then it's better to design the beam as a rectangular beam because the beam and the slab are not cast together. Sometimes the beam and the slab, the rebars, everything put ready, and we pour concrete and they cast together. So when they are cast together, then you can take advantage of the slab together with the beam and design them as a flange sections. So if in the construction process, beam and slab are cast separately, then we design the beam as rectangular sections. If beam and slab are cast together, meaning that monolithically between they are cast together, not separate stages, then we can consider design the beam as flange beam. So depending if the beam is interior, then it's T section. If the beam as the edge, it becomes L sections. So that is the consideration that we have to make. But in your design project, you have a choice. I think you can design that as a flange beam or you can design that as a rectangular beam. Okay. So flange beam, beam depending on where the beam is. Some of the beam really is rectangular shape. For example, here is a void here. So if this is a void here, then this beam will be designed as rectangular sections. Here, the beam, if it's the slab and the beam are cast together, then it becomes L sections. Here, interior here or here, where there are slab on both sides, then it becomes, we can consider that as a T sections. Okay. Now, when we want to consider flange beam, because we consider the slab together, so how wide the slab we can consider as part of the T beam or L beam. So that is the first thing that we have to look at, and this is to look at effective span. Okay, effective span of the beam and also effective span of the slab. And for flange beam, we need to refer to this clause 5321, effective width of flange, because how wide is the slab we can consider, we must follow this rule to determine the effective width. So effective width is determined using the equation as shown here. So B effective is B effective 1 plus B effective 2. What is this? The next diagram will show you figure 5.2 and 5.3 plus BW. BW is the width of the beam. Okay, it's called web section of the flange. So BW, and all this must not be more than B. So what is BW? What is B effective 1, B effective 2, BW? B is shown in the next diagram. Okay. So B effective 1 or B effective 2 is given by these equations, which is 0.2 Bi plus 0.1 L0, and this must be less than or equal to 0.2 L0. Okay, and B effective I must be less than Bi. So this is the equation that we use. And what is B effective and BW and Bi, and B is shown in the next diagram. Okay. So B effective 1, because if it is T sections, then you have one side here, one side here. So this is B effective 1 and B effective 2. And B effective is, of course, B effective 1 plus B effective 2 plus BW. BW is just, when you design for rectangular beam, is equal to the width of the beam. And B, what is B? B is the distance of center line of this side to the center line of this side here is called B. And what is B1 and B2? B1 is from the face of here to the center line is called B1. From this to the center line between this beam and this beam here is called B2. Okay. So this is the meaning of B1 and B2 or BI, where I is 1 or 2, and this is the meaning of B effective 1, B effective 2, or B effective I, where I is 1 or 2. Okay. And LO, okay? In the equation, LO appear here. So LO is given there, 0.85 L1. So what is L1? Is center to center distance. And LO, depending on whether it is at the end span or interior span or cantilever span, this LO has different formula. So LO here, definition of LO is, for end span is 0.85 L1. Okay. Okay. And here is 0.7 L2. Okay. And for that part is 0.15 L2 plus L3. Okay. So depending on different parts of the beam, so the definition of LO is calculated as shown in this figure 5.2 here. Okay. So from here to here, if we are looking at the flange here, design the beam is here. So LO is from this equation. If we want to design the flange as a flange beam located within here, so LO is given by this equation and so on. And if there's a cantilever, then you have to calculate. If there's a cantilever, then you have to calculate LO using the equations here. Okay. So this is where, yeah. So by referring to that figure, we can understand what is a B effective 1, B effective 2, B1 and B2, and what is the limit limit of B effective. B effective must not be more than B. Okay? And B effective 1 or B effective 2. B effective 1 must not be more than B1. B effective 2 must not be more than B2. Okay? And B effective 1 or 2 is calculated using this equation 0.2 BI plus 0.1 L0, and it must not be more than 0.2 L subscript 0. So there are a lot of rules that we have to follow in order to get the width of the flange first. Okay? So once we know the width of the flange, which is B effective, then we can do the design. We can carry out the design. Okay? Now, there are some basic formula that we need to know in order to design flange beam. So I will go to the design steps. I will go to the design step to share with you the design step. Okay. This one is design. Consider flange beam is in this design formula book is under section number 6. Design for flexural, and design for flexural start with rectangular section. These are the one that we have covered. And then you have design for flange sections. Okay. Design for flange sections after design for rectangular sections. Now, these are the steps involved, I think. Here we have the formula and also the dimensions of the flange. BW. BW is the width of the web, which is the width of the beam part. Now, B here in this design formula is the same as B effective. B here in this design formula is the same as B effective. D is the effective depth. HF is the flange, thickness of the flange, which is equal to thickness of the slab. HF is thickness of the flange part, which is equal to thickness of the slab. Okay. So the first thing that we calculate is, if we want to design as flange section class, is we calculate MF. MF is given by that formula. Okay. And there are some mistake here. Some mistype here in this formula. So this should be 0.567 FCK. 0.567 FCK BHF only, not BHHF. Okay. So there are some typing mistake here. So 0.567 FCK BHF. Then multiply with parenthesis D minus HF over 2, not H subscript F over 2. So this is not correct. 0.567 FCK BHF multiplied with D minus HF over 2. Okay. The B here, class, the B here is the same as the B effective. Is the same as the B effective that we tried to calculate just now. Here in this design formula book, the symbol P effective is equal to B. The B effective, the effective flange that we need to calculate just now using the code. So here in this section of this design formula book, the symbol used is B. Okay? And there's a mistake here, so I repeat 0.567 FCK BHF multiplied with D minus HF over 2. HF is the thickness of the flange, which is the thickness of the slab itself. Then there are two checking that we have to do to determine whether the neutral axis lies in the flange or neutral axis lies in the web. Okay. So that is the thing that we do next. After you calculate MF, then you compare your design formula, your design bending moment, MED, whether it's less than equal to MF or more than MF. Okay. If less than equal to MF, then neutral axis lies in the flange. So if neutral axis lies in the flange, the calculation is very similar to rectangular sections. So the next thing you calculate K, where MFCK B is the width of the flange, D is effective depth square. Then you calculate Z, the same thing as rectangular sections. Then you get the area of steel, the tension steel, AS M 0.87 FYKZ. So this is very similar to design of rectangular section if M is equal to less than MF. Okay? Meaning that neutral axis lies in the flange. Okay? If neutral axis lies in the web, there are more calculations that we need to do. So first thing, we calculate beta F. Again, there are some mistype here, class. This should be beta F equal to 0.167 BW over B plus 0.567 HF. Not HF over D, 1 minus BW over B multiplied with 1 minus HF over 2D. Okay. Then, after calculating beta F, you calculate N balance if for neutral axis lies in the web. So you calculate beta F first, then you calculate N balance, which is beta F multiplied FCK BD square. Then you compare M with M balance. Okay. What is this comparison for? If M is less than M balance, then this is singly reinforced, no compression reinforcement is required. So when neutral axis lies in the web, you need to calculate M balance, then compare with the design bending moment. If your design bending moment less than M balance, then only tension reinforcement is required. Compression reinforcement is not required. Then AS, tension reinforcement area, is calculated using these equations. Okay? If M greater than M balance, then compression reinforcement is required. Then you calculate compression reinforcement first using these equations. Then you calculate the tension reinforcement using this equation. Okay. So the steps is given here. So you have to first decide whether the neutral axis for this flange section lies in the flange or it lies in the web. This is the first step. Okay. So these are all the steps here. Calculate this, then compare this with this to decide neutral axis lies in the flange or neutral axis lies in the web. If neutral axis lies in the flange, the design is very similar to rectangular sections. The B here is not the B in the beam, yeah. The B is the width of the flange here. If neutral axis lies in the web, which is under these conditions, then you have to calculate M balance, then decide whether compression steel is required or not. If compression steel is not required, then calculate AS using these equations. If compression steel is required, calculate AS prime first, the area of compression steel, then you calculate area of tension steel. Then we have to check for also minimum and maximum area of reinforcement. Okay. You have to check for this also minimum area of reinforcement and also maximum area of reinforcement. So that is for design if your beam is considered as flange sections. Yeah? Flange sections. So the steps that you have to go through is you need to decide the effective width, then using this clause given. Okay, it is also given here, class. Now, the last thing that I want to cover before we end is when you have flange sections, the design for shear, vertical shear, is the same as rectangular section, exactly the same. When you design for vertical shear, it's exactly the same for rectangular sections because we assume the shear to be taken by the web. We assume the shear taken by the web sections, so the design for vertical shear is exactly the same for rectangular sections. Okay? But if there is a flange sections, then you have to calculate, you have to go through this a bit lengthy steps. This is to calculate transverse shear. Okay? Transverse shear. Now, class, the transverse shear is shear which is acting here between the intersection between the web and the flange here, represented by this arrow here. These are the transverse shear. This happens in flange sections, and we need to provide this shear reinforcement. We need to provide shear reinforcement in these directions to resist that transverse shear. And that reinforcement can come from the reinforcement in the slab. So this reinforcement is to resist transverse shear. Vertical shear is in the web here. We design the same as rectangular sections, but for flange you have this transverse shear, horizontal directions. And this has to be resisted by this reinforcement. This reinforcement which is located in the flange of the beam sections. So this is extra if to check for shear in flange beam. Okay, and the steps is quite complicated. Okay. So these are the procedure for calculating transverse shear reinforcement. First, you calculate VED, which is this equations. And what is delta FD? What is H? HF is the thickness of the flange. And what is delta X? So delta X is explained later. What is delta X? So you have to calculate VED first, which is the design shear stress. Then, if VED is less than or equal to 0.4 FCTD or 0.27 FCTK, then you no need to provide the transverse shear reinforcement. Okay. If it is more than this, then we have to check using this formula here. And we have to find this theta F. Okay, we have to find theta F. And theta F we have to do try and error. We check what is the minimum value theta f. If VED is less than that or more than that, then we have to check for calculate the actual theta f. Okay. So if this is more than this, then we compare this with this. But because there are theta f here, so we have to assume theta f first and compare. Okay. The lower value of the angle is tried first, and if the shear stress are too high, then we have to calculate the actual theta f using this formula. So the theta f has some range of the values. Is given here. If the flange is in compression, then theta f is between this and this. If the flange is in tension, then theta f is between this and this. So we have to try first with this and check if this is less than this or not. If it is less, then we take the lower value. If it is more, then we have to calculate the actual theta f. Then only we calculate the shear reinforcement required. ASF over SF by using this formula. Okay. So class, this one is involve more steps of calculation if you design for flange sections. But there are cases where you can take advantage of the slab. Okay. If you take advantage of the slab, then you can reduce the number of reinforcement required because the slab acting as a compression, as a big compression area, you can take advantage of that. But when you do that, then you have to go through these extra calculations for flexural reinforcement and for transverse shear, okay? Transverse shear, which is caused by horizontal shear force between the intersection of the flange and the web. And we need to provide shear reinforcement for that. Okay? That is the transverse shear. Okay? So, as I mentioned in the design project, you can take the beam, all the beam that you want to design as rectangular sections. Then the calculations just follow the design for rectangular sections. But if you want to take advantage of the flange, if you decide to take advantage of the flange, the web, then you can design that as a flange sections. Okay. So class, I think that's all that I would like to cover with you. And we expect that with the stages that you are in now, you should start with your beam design. Okay. So when you have problems, please, you can always discuss first with the respective supervisor of your design project, or if you have any questions, then please let me know. Okay.